In this lesson, we will examine how direct current electrical motors work. An electric motor is a machine for converting electrical energy into mechanical energy. Its function is therefore the reverse of that of an electrical generator, which converts mechanical energy into electrical energy. The 3D circuit you can see here is the same circuit as that represented by the circuit diagram. The left-hand section of the circuit diagram represents the stiff wire in the form of a U. This section is hinged at either end to allow it to swing freely. If the circuit is switched on, there is no visible effect. You know, though, that the wires through which current is flowing have an accompanying magnetic field, and that this magnetic field is in the form of concentric circles. If we switch the circuit off and introduce a large horseshoe magnet, again nothing seems to happen. The wire does not move while the circuit is broken. But if the circuit is now remade, we observe a startling effect. The wire springs out from between the magnet and hovers in mid-air, supported by some unseen force. The force is produced by the combined magnetic fields of the horseshoe magnet and the current-carrying wire. You will recall that the lines of flux between the two poles of a magnet look like this, and that the magnetic field around a current-carrying conductor looks like this. If the current-carrying conductor is placed between the north and south poles of the magnet, the two sets of magnetic fields will interact. In the area where the fields are running in the same direction, there will be a strengthened magnetic field. And in the area where the fields oppose each other, the field strength will be reduced. This will produce a force trying to move the conductor in the direction of the weakened field. This is the basic principle on which electrical motors operate. We are able to predict how any two magnetic fields will interact in any given situation, and for any direction of current flow, by using a method known as Fleming's left-hand rule. Let's look at how this rule works. Hold your left hand in exactly the same way as the hand you see on screen. Each of the three fingers shown here points at right angles to the other two fingers. The fingers represent the direction of current, direction of magnetic field, and direction of the resultant force. The second finger represents the direction of the current flow. The direction of current flow we are talking about is that of conventional current flow. That is, from the positive terminal to the negative terminal. The letter C in second should help you remember that your second finger represents current. The direction of the magnetic field is represented by the first finger. Think of the F of first as also standing for field. The first finger points in the direction from North Pole to South Pole. You are indicating the lines of force of the magnetic field to which the wire is exposed, not the magnetic field that the wire itself is generating. Your thumb will now indicate the direction of motion of the resultant force. The device shown here is a simple basic electric motor. The component in the center consists of a coil of wire wrapped around a wooden block, which is free to rotate. But what makes the block and coil rotate? To explain this phenomenon, we will consider the case of a single loop of wire. This is the magnet and loop viewed as a cross-section. The current in the cross-section of wire on the left is flowing out of screen towards you. The magnetic field produced by the permanent magnet acts from left to right. Fleming's left-hand rule tells us that the resultant force pushes the wire on the left upwards. If we apply the rule to the right-hand wire, which has its current flowing into the screen, we see that the resultant force acts in a downwards direction, which is what we would expect if the loop is to rotate. Notice the shape of the magnetic field around the wires. If you imagine the magnetic field lines to be rubber bands under tension, the wires of the loop are about to be catapulted in the directions that we have just predicted using Fleming's left-hand rule. The resultant forces produced by the interaction between the magnetic field in the loop and the field of the permanent magnet will turn the loop around in a clockwise direction. But what happens when the loop goes past the vertical position? The forces acting on the loop now act in an anti-clockwise direction, pushing the loop in a direction opposite to the direction in which it started turning. With the mechanism operating as we show here, the loop would rock back and forth until it reached a vertical position where the forces were pushing it in neither one direction nor the other. To be of any practical use, a motor needs to keep on rotating. This electric motor keeps on turning because it is fitted with a device called a commutator. The loop of wire that we have just been examining comes to rest vertically because, as it passes through the vertical position, a force begins to act on it in the opposite direction to the force which caused it to start rotating. But the direction of the magnetic field around a wire depends on the direction of current flow. So if the current flow can be reversed as the loop reaches the vertical position, the resultant force due to the interaction of the two magnetic fields will also reverse and cause the loop to continue rotating. The commutator in an electric motor ensures that the current reverses in this way. This is what a simple commutator may look like. The wires are fixed. They do not turn as the axle rotates. They brush against two curved strips, which serve as electrical connections to the coil. As the axle turns through 180 degrees and passes the vertical, the wires or brushes reverse the connection of the coil to the terminals of the power supply, thus reversing the direction of the current in the coil. Therefore, the loop continues to rotate. The parts coloured grey are insulating components. They are in contact with the brushes when the coil is in a vertical position. Thus, in this position, no current flows through the coil. If the direction of the supply current is reversed, the motor will rotate in the opposite direction. Similarly, if the magnetic field polarity is reversed, the motor will rotate in the opposite direction. However, if both are reversed, the direction of rotation of the motor remains unchanged. That is the end of the lesson. Here are the main points to remember. If a wire carrying a current lies at right angles to a magnetic field, the wire experiences a resultant force. Fleming's left-hand rule enables us to determine the direction in which the force acts. The second finger is used to represent direction of conventional current flow. The direction of the magnetic field is indicated using the first finger. The direction of the resultant motion will be indicated by the direction in which the thumb is pointing. To keep it rotating, a DC motor needs a commutator to reverse the current flow every 180 degrees. The direction of the motor can be reversed by reversing the direction of the supply current or the direction of the stationary magnetic field.